Hello and welcome to a new video. This is for Precalculus using the Math UC curriculum. We're on lesson 27, which talks about geometric sequences and series. So this definitely goes along with last lesson, lesson 26, which was talking about arithmetic sequences and series. This is a slightly different kind of sequence or series. So what kind of sequence or series is it? If you remember, an arithmetic sequence had to do with adding the same number to get each of the next terms. A geometric sequence is different because instead of adding a common difference, like in an arithmetic sequence, we're going to have something that we're multiplying by to get the next term. And so instead of calling it a common difference, since difference implies subtraction, we call it a common ratio. So a geometric sequence is a sequence where consecutive terms have a common ratio. Another way of thinking of that is they have a common factor. Here's a really relatively simple example here, 2, 4, 8, 16, 32. In this example, to get each of the next terms, we are multiplying by 2. Not adding 2, we're multiplying by 2. So we'd have to times 2, times 2, times 2. So one of the things with this is that we can get to really big numbers really quickly, depending on what our starting term is and what we're multiplying by each time. But just to make sure we understand, because one of the questions in the workbook is to define what the common ratio is. It's for a geometric sequence, it's the number that you multiply by to get the next term, would be one way to put it. It's the, to get it, if you have a sequence, we would take the second term and divide it by the first term, or we could do that with any two consecutive terms. But we need to do like 4 divided by 2 to figure out what it is, not 2 divided by 4 for this example that's on the screen right now. So that's the idea about geometric sequences. I find geometric sequences overall seem like they go pretty smoothly because we're using all of the same notation and terminology from arithmetic sequences. So hopefully you got it all figured out when we were dealing with kind of easier sequences where we're just adding. Because then geometric sequences are a little bit trickier as far as the formulas we have that go along with them. We have here 3 formulas, and really we're mainly just going to need to use the first one for what we're being asked to do in our workbook. So to find the nth term, which another way of putting that is to find a specific term of a geometric sequence, we use this formula right here. So a of n, remember, if we are trying to find like the 5th term, then that would be a5. So n would be 5. Then that equals a1, means whatever the first term is, or starting point. And then we would times that by r, which is the common ratio, to the n minus 1 power. And so there is a little bit of possible trickiness here for when you're putting it into the calculator, because we do want to make sure that n minus 1, either that we go ahead and subtract it ourselves since it's just minusing 1, or that we make sure that the n and the minus 1 is in the parentheses. Back in the day, with the old TI calculators, you had to put parentheses around the exponent. But for most, if not all of you, when you're putting it into your TI calculator, when you raise it to an exponent, it stays as an exponent until you actually press the arrow over button, which is great for this case. Desmos, however, you need to be careful, because at least whenever I'm doing it on the computer, if I raise it to a power, sometimes it will just automatically drop back down to a normal number. And so I have to like make sure that I either put parentheses around the exponent on Desmos, or just pay attention to make sure that it's still up in the exponent. I don't know. You'll see what I mean, I think, later on, I'm sure. So let's see. The next formula, if we wanted to find the sum, just like we had a couple of formulas actually for the arithmetic series, if we wanted to find the sum of the first n terms of a geometric series, we'd use this formula right here. This is a much more complicated looking formula, in my opinion, than either the first formula on here or the formulas we did last time. And it's because just this is more complicated in some ways. Instead of us trying to add together things that have a common difference, right? We're adding together things that have a common ratio. And so we end up having to kind of do some division here to figure out like what's happening. But you can use that if you know like the first term and the common ratio, or if you can find those. But in the same way that in last lesson I talked about that we could just put the sums they gave us into the calculator, the same thing's going to happen to us here. And in fact, because of the way the sums are written, I think it's way easier just to put it into the calculator because it's not actually really obvious what A1 and R would be in some of them. So I think it's worthwhile to go ahead and just use the calculator for this. Let's see. This last one is not, I don't think, mentioned in this section at all, but there's an interesting thing that can happen with geometric series that doesn't happen with very many other series, that we actually can add up an infinite number of terms of a geometric series, and we can actually get an answer if the common ratio is something that is between 0 and 1. So basically, if we multiply by a fraction, like 1/2, then you actually could end up figuring out how much those add up to be. And instead of making a really long tangent here in this video, I think I'm gonna attempt to make a separate video at some point that has to do with this, because I think it's a really cool concept. It is definitely, though, a simpler formula if you were trying to do that, but it only works in some cases, not in all cases. So let's look at some examples. So example 1 here, find the first 5 terms of the geometric sequence. We're given the first term on each of these, so that's nice. This would be 5. And then we're given the common ratio. And so what we're going to do is we're going to say, I need to multiply by 4 to figure out what the next term would be. So 5 times 4 is 20. Times 4 again is 80. Times 4 again is 320. Times 4 again is maybe something I don't want to do in my head. No, it's fine. 1280, I think. I feel pretty confident about that. That should be the first 5 terms. It's just multiplying by 5 to get each of the next terms. What if we have, A1 is 6, but then R is a third? So we're going to say 6 times 1/3, which is like saying 6 divided by 3, so that's 2. And then after that, actually, this gets kind of annoying because 2 times a third is 2/3, and we're just going to get smaller and smaller fractions. Incidentally, that is why, if we wanted to, we could find the sum, the infinite sum of this sequence, because we would keep adding smaller and smaller pieces to it. So like timesing 2/3 by 1/3 would be 2/9. Have to remember how to multiply fractions or use a calculator. Then times 2/9 by 1/3, so that's gonna be 2/27. And it would just keep going like that, getting smaller and smaller fractions if we were to continue it on. All right, so example 2, and I've got a couple examples actually that are the same format here. So example 2, find the 20th term with A1 equals 3 and R equals -2. Now this is a situation where I would not want to find all 20 terms. Personally, I would not. So we're going to use that formula from earlier that said AN equals A1 times R to the n minus 1, because we know the first term, we know the common ratio, and we know n because we're trying to find the 20th term. Now, chances are you're going to want to use a calculator in some form or fashion here, because I personally do not want to figure out what -2 to the 19th power is. That's just not something that sounds great to me. So let's see. So we're going to do 3 times. Now when I do this, I need to put -2 in parentheses, because if the common ratio is -2, then I'm taking that common ratio -2 and I'm raising all of that to the power. So here's what I was talking about earlier. Either I can just say, oh, I know what 20 minus 1 is, and type in 19 here. Or if I want to really let the calculator do it all by itself, then I can do 20 minus 1. But see how Desmos just moved over, and that -1 is not in my exponent? So for Desmos, we need parentheses around our exponent. Because I think because Desmos thinks it's much more likely that you would want to have the -1 be out to the side than in the exponent. I don't know what that's about, but yeah, it's just really important, since our calculators these days are all about like making it look like what we're writing, that you make sure it actually looks like we're writing. That -1 should be up in the parentheses. Or just use 19 instead, whichever. It's a really big number. Negative 1,572,864, which I'll totally remember. Negative 1,572,864. Negative 1,572,864. Is that right? Yeah. I have the hardest time remembering numbers, which is super duper ironic, right? Because I'm a math teacher. But hey, whatever. So that's this example. There were some problems like this with the arithmetic series that hopefully you figured out how to deal with. Instead of them telling us the common ratio, they're just telling us the first two terms. But that means that we can find the common ratio by taking the second term, 5, and dividing it by the first term. So without too much trouble on this, I can figure out, okay, the common ratio is a half. So then I need to find the 40th term, which is going to be the first term times 1/2, which I'm going to go ahead and put this in parentheses and then put that to the n minus 1. So 40 minus 1. So now that I can just edit this a little bit if I want to. So make sure that you put parentheses around the 1/2. I feel pretty confident that I need those. I just realized this may be too big of a number, or I mean too small of a number. Yeah, because it's not letting me change this to a fraction. I wonder what I would have to get to be able to change this to a nice fraction. Wow, that I would not say that that's a nice fraction. It's a rather large fraction. Whoa. So the deal is that we're just getting, in this case, this is the actual, like, if I did this, this would be the 20th term, is this really small number, right? So I think that's what I'm going to choose to do, is I'm actually going to go back and edit this and make it be 20th term instead of 40th term. So let's pretend it wanted the 20th term. So 10 times a half to the 20 minus 1 equals 5 over 262, 144. 5 over 262, 144. So that's the 20th term. So you gotta watch out. If you're making problems, at least, you gotta watch out, because these problems with geometric sequences, your numbers either are gonna get really big or really little pretty quickly most of the time. So now here is a sum that we're gonna type in. And so to do this, remember, you go to math on your TI calculator and you scroll either up or down until you see the word summation, and it has a sigma like this. And when you do that, then it pops up with like a template for you to fill in. And Desmos actually does the same thing. You just press the keyboard and go over to functions and miscellaneous and then pick the sigma. And whatever letter you put here, like Desmos has in, just needs to be the same letter over there. I can actually change it to K if I want to, and on your TI calculator you can use K by looking up above the buttons at what the letters are. Or I could just use X, or I could use whatever letter I want. So make sure that you pay attention. This started at K equals 3. So if we were finding this by hand, what we would need to do is start by plugging in 3 and then plug in 4, then 5, then 6, and do that all the way to 10. I'm going to go ahead and put parentheses to make sure that it does this the way I want it to. 4 to the, I'm going to put parentheses again. Actually, I don't think I needed the bigger parentheses there. K minus 1. Because I did it earlier and I didn't have parentheses and it gave me the same thing. But the parentheses up here was so that it would put the minus 1 inside of the exponent. So if you add all these together, you'd get 349,520. And so my reason, by the way, for saying that using the formula is going to be a lot harder on this is that we're not starting at the first term. We're starting at the third term because K is 3. And this formula looks pretty close to our formula for a specific term. There's not another number up here. So A1 actually would be 1, because we could say this is 1 times 4. And the common ratio would be 4. But looking at the other, some of the other sums they give you, it's actually a lot harder to figure out on some of them what your first term and common ratio are. So my suggestion is just to put it in the calculator, because that's fun. I think it's fun, personally. So this equals 349,520. And there we go. Thank you so much for watching. I hope that you'll leave me a thumbs up, either because you liked the video or you like geometric sequences and series. Maybe you just like me and think I'm a really cool person. Maybe you like the I think you would like me. Maybe you like Super Mario. I don't know. It could be whatever. We have a lot in common, I'm sure. Also, hopefully newly added, there's now a like join or subscribe button down below. If you would like to show some support to my channel, you can click that button and give me some support and also get some perks in return. So like I said, thanks for watching, and I'll see you in the next video, lesson 28.